Everybody, welcome to Beyond the Boundaries, innovations set to transform the way we live, work, and play. My name is Janita. There's a slide here for me. And I'm a member of the UQ Young Alumni Board and lead of the Young Professionals portfolio. And it's great to see all of you here tonight. I'm very much looking forward to this. Before we begin, I would like to acknowledge the traditional owners of the land on which we gather and pay my respects to elders past, present, and emerging. We extend our respect to Aboriginal and Torres Strait Islander peoples here today as well. Just a little bit about us. I'm proud to serve on the UQ Young Alumni Board for the Young Professionals portfolio, alongside my fellow board members, Alicia, Hayden, and Rena, who are all here. If you are here, put your hands up so you can see where they are. Rena's back there, Hayden's over there, and Alicia is just about to go outside there, which you'll meet later today. Our purpose is to foster a vibrant community of young alumni, support professional development, and create opportunities for networking and engagement. We're dedicated to helping you thrive in your careers and connect with the incredible network of UQ graduates. So tonight's event will feature five amazing UQ researchers who will share their groundbreaking work with us. Each presenter will have about 8 minutes to pitch their research, followed by a panel discussion where you can ask your questions. And throughout the presentations and also during the panel discussion, please do submit your questions via Slido. You can either scan the QR code on the screen there or go to slido.com and put in the code UQ alumni, and you should be able to submit your questions there. And because you are, and for the people who are in person here, you will get a chance to also raise your hand and ask questions on the floor as well. So it is my pleasure to introduce our first speaker, Dr. Hannah Leeson. Dr. Leeson is a research fellow at the Australian Institute for Bioengineering and Nanotechnology. She's working on one of the final frontiers of human physiology, understanding the brain. Using brain organoids or mini brains, Dr. Leeson is exploring how the brain works and how this knowledge can be combined with personalized medicine to develop therapies for rare neurological diseases. Please welcome Dr. Hannah Leeson.
Hello, thank you for the introduction and thank you for inviting me along. It's very exciting to be here. So yes, I'm a neurobiologist and stem cell researcher at AIBN. And today I'm going to talk about how we can use these lab-grown brain models to look for some treatments for some of the rarest neurological diseases. But first, First, I want to introduce you to somebody who is really very special. So this is Tallulah Moon, and she has a very rare form of hereditary spastic paraplegia, which means that she's not able to walk or to speak. Now, her parents approached us about 2 years ago, hoping that we would be able to help them to find a treatment or a cure to help Tallulah. So where do we begin with this challenge? We have to first figure out what's going on, but the trouble with studying the brain is that it's really difficult to get an understanding of what's going on. So for starters, it's phenomenally complicated, right? We've got over 100 trillion synaptic connections there. So not only do all of those have to all work together to drive our body, but they're also responsible for our perceptions of our surrounds, our emotions, personality. So not only that, the brain is also quite inaccessible. So we've all got our big bony crash helmets on with us all the time, which, I mean, generally in day-to-day life, skulls are pretty handy. But when it comes to visualizing the brain, the skulls can get in the way. Samples is another thing that's quite difficult to come by. So I bet that there's not a single person in this room who would let me just take a scalpel to your brain, chop out a piece so that I can see what's going on. So to overcome these challenges, we can use stem cells to create brain organoids or mini brains. Now, all that I need to do this is just a drop of blood or a little bit of skin from the patient. Now, every cell in the human body all has the same DNA. So it only depends upon what genes are turned on or off as to whether a cell is a stem cell or a brain cell or an eye cell. So by turning on specific genes from some cells of the blood, then we can create these induced stem cells. Now, stem cells are unique in that they can become any cell in the human body, like brain cells or neurons that I'm showing here in the corner. For my purposes, I want to create brain organoids. So this is a 3D structure. So the brain organoids develop quite similar to how a fetus's brain would develop, but because there's no blood vessels in this system, then they'll reach a maximum size of about 2 millimeters. And when we stain for different components of the brain, we see that our organoids can contain all of the same cell types that our brains do. So we've got neurons and we've got supporting cells like astrocytes and other glia. We also have some immune cells in there as well. And all of these are organized into structures that resemble parts of the human brain, like the folds of the cortex that I'm showing here. So altogether, this means that organoids are a pretty good model to help us study rare brain diseases. So because they contain all of the same DNA as the patient that we made them from, then organoids will capture features of that patient's disease. And this lets us test for treatments that are going to be specific for that patient. As an example, in our lab, we're using these organoids to look for treatments for patients with drug-resistant epilepsy. So these brain organoids have electrical activity, just the same as our brains do. And using electrodes, we can measure seizure-like events that are happening within these brain organoids. We can then treat the organoids with various anti-seizure medications to find the most appropriate drug or combination of drugs that's going to work for that patient. Another example of how we're using these organoids in the lab is to investigate multiple sclerosis. So these organoids contain the myelinating oligodendrocytes, and that is the very specific cell type that is affected in MS. So these models are helping us understand disease progression there as well. So this brings me back to looking for a personalized treatment for Tallulah. So in her disease, SPG56, it's caused by mutations in just one single gene, right? And that results in a missing or non-functional copy of the protein there. So what we are attempting to do is to use a viral vector to deliver a working copy of that gene. Now, that working copy of the gene will then produce a functional protein, and we're hoping that this will restore neuronal health. So this is what we're testing in Tallulah's brain organoids. And we can see this gene delivery system working in real time. So by including a little green tag just in front of the gene that we're trying to deliver, we can see when and where the correct copy of this gene is being delivered inside Tallulah's brain organoids. So obviously, safety is one of the most important things for us. So at the moment, we're doing trials to make sure that the treatment is going to be safe. We're also looking at efficacy. And we're also doing mouse trials at the moment. If all of this goes well, then next year, it's looking like Tallulah will get her very own personalized therapy. So I just want to conclude by saying that the future's looking pretty good for people with rare neurological diseases. All the time, we're coming up with brand new models to help us study disease pathologies. We're coming up with safer ways to deliver genes and also ways to target that gene delivery specifically to affected organs or affected cell types. And all of this is working to really improve patient outcomes, hopefully for Tallulah, but also for thousands of other people out there with rare neurological diseases. So I really need to thank my awesome lab mates and also the awesome families that I work with. It's a pleasure. Thank you.
Thank you so much, Dr. Lathan. What a fascinating presentation and very actually close to my heart. I was diagnosed with trigeminal neuralgia about 3 years ago, and just understanding what my nerves are doing, where they should be and where they're trying to go and do what they're doing is beyond me. I'm glad that we have doctors like you to be working on that, because it's definitely some very complex work that you're doing, and with great benefits and advantages leading towards the future. Now, I would love to introduce Dr. Colin Hallett. Dr. Colin Hallett is a senior research fellow in cosmology from the School of Mathematics and Physics. Dr. Hallett's research involves creating enormous 3D maps of millions of galaxies to understand what the universe is made of, how it was formed, and how it might look far into the future. So please join me in welcoming Dr. Colin Hallett.
Okay, can everyone hear me? This is the first time trying this microphone. Good. Okay, good. So yes, my name is Dr. Colin Hallett from the University of Queensland, and I'm going to talk to you today about our work mapping the cosmos. Astrophysics and astronomy is not always the most accessible thing. We often deal with enormous scales. So the way I'm going to start this talk is by trying to bring it home a little bit. So hopefully this kind of picture is not a surprise to anyone in the room. This is a map of Australia. We are kind of here. I'm not a geographer, so I actually don't know if we're here, but I do know we're here on Earth. And Earth is one of 8 planets which orbit the sun. This is the size of Earth relative to the size of the sun, although the distance isn't to scale. However, you know, if you look at the night sky and you look at constellations up there, you can see that actually the sun is only one of billions of stars in billions of galaxies throughout our universe. And so what I'm going to talk to you today is how we're going to map those galaxies and use them to understand how our universe has formed and evolved over time. And so we can use these maps to understand, the formation and evolution of the universe over its entire lifetime, the last 14 billion years. Okay, so in particular at UQ, we're involved in a bunch of different surveys using telescopes all around the world. For instance, there's a couple in Chile. This is a survey called the Dark Energy Survey on a telescope in Chile. This one is still under construction. This is an artist's rendition of what that telescope will look like. There's telescopes in Western Australia. For instance, these are radio telescopes on a survey called Wallaby. And there's telescopes in the USA, which we use as well. And in particular, today I'm going to talk a little bit about the Dark Energy Survey in Chile and the Dark Energy Spectroscopic Instrument in the USA. Spoilers, they both contain the word dark energy in there. That's a hint for the future of this presentation. And so to begin with, let's talk about DES, the Dark Energy Survey. So surveys such as DES allow us to image the sky. The way we do that is we take telescopes like DES, which have mirrors, which are enormous. Quite frankly, this mirror is about 4 meters across. That's about here to maybe where those chairs are. And it's a single piece of glass, perfectly polished. It takes about 6 months to make these things. And then what we do is we take that mirror, we go, wow, this is a great mirror. And so we stick the world's biggest camera on that mirror. And so we've used, over the last sort of 10 years, this 4-meter mirror alongside a 570 megapixel camera to take pictures of the sky. What we do is the way these cameras work is it actually just says yes or no if a bit of light hits the camera. So what you can do is if you want a color image, you can put filters in front of that camera and you can observe the sky in different colors. And so we've done that with these 5 filters here we call U, G, R, I, and Z. U is ultraviolet-ish. R is kind of reddish. I and Z are more reddish, actually towards the infrareds. Astronomers are not known for their ability to name things. So that's just what we're left with, unfortunately. And if you do that, you get something which looks like this. This is a real image of the sky as taken by the Dark Energy Survey. And each of these is a little camera, and combined, they make up 570 megapixels. And if you do that and you put it online and you process the images, you get something which looks like this. So all the data from that survey has now been taken and is actually fully accessible online. If you go to this website, legacysurvey.org, you can move around the sky yourself. You can look at these images. And it's an amazing data set in its own right. We've used it for tons of science, and people are still using it for science today. However, what I'm going to talk to you about is basically, this is only the first step of the process. So what we do once we have these images is we go, there's some really interesting things in here. For instance, can anyone see a galaxy? Yes, this big thing here. This is a galaxy, of course. But in fact, what we do is we run sophisticated algorithms on images like this, and we go, where are all the interesting galaxies? And it turns out they're here. So this is all the interesting galaxies found in this image. And that's just not all the galaxies. There's in fact way more galaxies than just the circles here. These are the ones that we've identified as interesting enough to follow up for further study. And in fact, if you count how many galaxies the Dark Energy Survey has found, it's over 543 million. So that's a lot. And that's only over 1/8 of the sky. So if you multiply that by 8, that's at least how many galaxies there are in the universe. Each of these is going to contain hundreds of millions of stars. Suffice to say, there's a lot of stars and a lot of planets in the universe. But with surveys like DESI, what we're actually doing is trying to map the 3D positions of these galaxies. And we're trying to map up to 40 million of those over the next few years. So how are we doing that? So this is where some other interesting technology comes in, and it's this technology here. So what DESI actually is an instrument which contains 5,000 robotically moved fiber optic cables. So the way this works is each of these is a tiny little robot which rotates, and when you point that telescope at the sky, you can rotate those fibers and you can place them on any galaxies of interest. Each robot carries a fiber optic fiber, which is about 1.5 times the width of a human hair. We stick them all together like this. And apologies if any of you have trypophobia. I've heard that this triggers some people. But what that means is that we can place 5,000 fiber optic cables on 5,000 galaxies at once. We can observe the light from those galaxies, and then we can use that to work out how far away the galaxies are as well. And then the end result is something like this. So this is a map of actual data from the first 2 months of the DESI survey. Each dot here is an actual galaxy observed from the Earth. And then you basically ask, where is the galaxy on the sky and how far away is it? And you can see this amazing 3D map of galaxies in the universe. And our analysis of these maps actually shows that space, I'm sure I don't need to tell you, is pretty big, pretty damn big. And each of these galaxies we're flying through is a real galaxy observed as part of these maps. We've taken the real image and we've overlaid it on top. And you can see there's a huge amount of structure in these maps. There's these big clusters of galaxies. We call them clusters. There's also what we call these sort of filaments, these tendrils of galaxies that connect the clusters. And then in between them are these kind of empty void regions that we call voids. Okay, and so that structure actually contains a huge amount of information about how the universe formed and evolved. And one of the stark and amazing things that we've really found over the last, 10 years that we've been doing this is that 95% of the universe is actually made of dark stuff that we can't see and is not those galaxies. And in particular, about 25% of that is called dark matter. It's stuff that acts just like normal matter that we find here on Earth, but and it acts gravitationally in that it pulls things towards it and it pulls galaxies towards it, but it's dark. It doesn't emit light. It doesn't interact with light in any way. The other 70% is something called dark energy. And actually, this part is really interesting because it acts almost like anti-gravity. What dark energy does is it seems to make the galaxies move apart faster than if it wasn't there at all. And so this is kind of like, anti-gravity is the best way to describe it. And the most interesting thing is it makes up basically 70% of the universe. It's the most dominant component of the universe today. And we actually have no real idea what that is. So we have no idea what dark matter is, no idea what dark energy is, and it makes up 95% of the universe. And so the idea of these maps, and the reason we're carrying out ever bigger surveys, is to try and understand the properties of dark matter and dark energy. And we can understand their properties both in time and the impact they have on the galaxies and the impact they've had on the evolution of the universe as a whole. And maybe one day, if we work out what dark energy is, we can also harness it for new technologies. I only need to tell you that anti-gravity would be cool. So if we can understand what dark energy is, maybe we can invent new technologies which implement it. And so that's all I had to say for today. If anyone has any questions about the details, please do come and talk to me later. Thanks.
for that incredible insight into our universe. I can't wait to see some of the questions that come through for you in the panel discussion. I think that will be quite interesting. Our next speaker is Skye Doherty. Oops, sorry, a sec. It's Skye Doherty, a senior lecturer from the School of Communication and Arts. Dr. Doherty uses creative and design-based research approaches to investigate alternative futures and tackle complex problems in journalism, law, education, and disaster resilience. I hope I got that right. Let's give a warm welcome to Dr. Skye Doherty.
Thanks. Thank you for having me. I'm going to bring us back down to earth quite rapidly, I think, after that. Unfortunately, I've got to use notes. I want to talk to you today about futures and building the preferable future or a preferable future that we would want. To do that, we need to be able to imagine that. And that can be very difficult when our news and our politics is full of problems that seem pretty much unsurmountable most of the time. Climate change, conflict, inequality, political extremism. These are just some of the things that are intractable and we're talked about constantly. A technical or a policy situation or solution on this hand is going to lead to another problem, a different problem on the other hand. We need fresh and creative and sometimes probably some radical ideas. And we need to be able to imagine a future and imagine and understand steps we need to create and get to that future. This is not about fantastical futures like this one. It's about visions of the future that are accessible and that are accessible from where we are right now. So tonight I want to tell you about Wicked Thinking. This is an experimental magazine project that uses practices from journalism and design to envision alternative futures. Wicked Thinking publishes news from the future. It takes complex problems such as bushfire resilience and forced migration, and those of you in the room have got some examples on your tables. And it imagines how things could change and the consequences of some of the decisions we might make in order to change them. The stories are a form of envisioning, one that I call speculative news. And these are stories that aim to provoke thinking about what society might look like and how it might respond to some of the challenges that we face. It's a way of envisioning futures that account for people, politics, problems, and the systems and structures that we experience day to day. So envisioning is not, I'm a journalist by trade, and envisioning is absolutely not a practice that we engage in. It's not associated with journalism. Daily news is concerned with reporting facts, documenting the events of the day, and getting things on the record. Journalists care about yesterday, today, tomorrow. They don't care about 10 or 20 or 50 years into the future. But news is a very effective way and a very effective interface for telling people about society and about our world. And so it's a very effective way of communicating about the future. Now, creative writers, futurists, and designers are a lot more comfortable with tackling and taking a longer-term view than journalists are. And they use a bunch of different types of techniques to envision different kinds of futures and build a picture of a preferred society. World building, future scenarios, which is a really strategic and methodical way of horizon scanning and analysing trends to be able to predict the future. But some envisioned futures are more plausible than others. Futurists create scenarios, science fiction writers create completely imaginary worlds in which imagined characters play out and tell us stories about quite implausible futures. Designers are somewhere in the middle of this. They prefer to explore possibilities, some of which are desirable, some of which are speculative, and some of which are preferable or even provocative. One technique, and one that I've used in this project, is the technique of design fictions. And these are stories or prototypes or provocations that tell of situations in which imagined products are used and the consequences of using them. As speculations, design fictions are really grounded in reality, And this is where I see very fertile ground for journalistic techniques and that approach to storytelling and research and documenting. Because speculative news is able to leverage a journalistic aesthetic that communicates to us ideas of trust, objectivity, and what is happening in the real world. So there's been 2 issues of wicked thinking published so far this year. As I said, it's experimental. The bushfires one is just off the press. I literally picked it up from the printer on the way here. And you can take these copies away with you if you like. But both issues are collections of future dated news, and they blend fact and fiction. They are both informed by research projects at UQ, and they draw on interviews, observations, literature surveys, and futures workshops, which are collaborative and based on co-design. So the futures of forced migration, those of you on the tables will have a copy of this, but for those of you at home, here's the contents page. So it grapples with issues of how digital technologies might be used to support increasing flows of displaced people into the future. Now, by some estimates, 1 billion people will be displaced by the year of 2050. That's globally. But how we deal with such large-scale migration is a challenge. Already, governments and humanitarian agencies are using databases, biometrics, artificial intelligence, and identity software to process individuals, but also to tailor and deliver support to them. These people are at once reliant on these technologies to build their lives and access services, but are increasingly surveilled by it. So the speculative news in these stories aims to grapple with some of these issues. It explores issues of freedom, efficiency, trust, security, and how these might play out over the next 20 years. So there's 6 stories in that issue, dated between 2028 and 2043, and they tell a bunch of things. A public backlash against Western governments, against using AI to distribute services to people who've lost their homes in a flood. Of nomadic populations who are demanding the same rights as displaced people and conflict refugees because a digital system is working so efficiently for these people. Or of a consent-based AI refugee management system that is working, a consent-based refugee management system, because at the moment there's no consent, or the emergence of disaster-resilient enclaves for the super rich. These are all based on trends that are happening in our world right now. The bushfire issue tackles the challenge of living in a more fire-prone environment. Hotter and drier conditions are already leading to more intense fire seasons, both here and in places like the Arctic. The costs of recovery are becoming unsustainable in some areas, and our assumptions about people being able to evacuate and insure are becoming increasingly untenable. Responding to these kinds of disasters is a massive challenge, and it's expensive. But the UN wants more effort, not placed on disaster response, but on preparation and resilience. Governments want individuals to share the responsibility for living there. They want them to take responsibility for the risks and the rebuilding afterwards. And insurers want people just to move to less risky places. But anyone who's tried to buy a house lately or rent one will know that there's this housing crisis that makes that a very difficult situation. So there's no easy solutions to these things. So there's 7 stories in that issue, and they range between 2029 and 2095. And the last one is about black holes, which I'm sure you might have something to say about. But for instance, communities and governments working collaboratively to manage landscapes. The factors needed to force attention into the environmental health, which has a direct relationship to the flammability of the environment. Alternative measures of success that don't just include loss of lives, but includes the consequences of people losing their homes when agencies are thinking about evacuating people, or radical insurance policies, or new social contracts. Some of these futures are utopian, some of them are dystopian, and some of them are completely mundane. The aim is not to predict the future, but to provoke you as a reader to envision how to build a new one. The stories are totally grounded in reality. They're informed by journalism and research processes and they reflect the insights of the people we interviewed and who were involved in our participatory workshops. They totally take a journalistic aesthetic. They're written in a hard news style with direct quotes, and that leverages that aesthetic, as I mentioned, of trust and objectivity. The quotes, some of the quotes are real and some of them are made up. But what I have done is that I've avoided using names so that the stories focus on underlying issues and structures, not on personal experience. I'm sure you're all familiar with all the news in your feeds at the moment, which is the experience of one particular person that doesn't talk to the bigger issue. So speculative news is neither fact nor fiction. It occupies a middle ground where imagination meets reality, where we can tackle wicked problems and change conditions and change values and priorities and imagine how that might play out. It's a way of asking how things could be, and is that desirable? If it is desirable, how do we move towards that future? If it's not desirable, how do we make sure we don't end up at that future? Wicked thinking is a provocation to shape the future actively. Thank you.
Thank you so much, Dr. Doherty. The power of words, really, and how that can help reimagine our futures and the wicked problems that we are looking into the future is pretty spectacular. And research that is a very complex one as well. Now, thank you, Dr. Doherty, for that. Now, please welcome Dr. Maxime Cordial, a senior lecturer from the School of Electrical Engineering and Computer Science. Dr. Cordial aims to transform data interaction by leveraging virtual and augmented reality technology, crafting immersive experiences that enable users to navigate data more effectively. Let's hear from Dr. Maxime.
Thank you. Thanks for the introduction. That's a pretty wordy title, so I'll try to unpack that as simple as I can. So I just want to start with just trying to describe the type of research that I do. So I'm a human-computer interaction researcher. So I'm interested in how we can, leverage technology to work better with complex problems. And I'm also a data visualization researcher, which means, well, we live in a very complex data-driven world. We've seen pretty cool examples with brain disease or exploring the universe. All that stuff is data, right? And we need to understand that. And the thing is, primary displays we use are tiny little screens. We can do like hardcore things, like trying to understand the universe, trying to understand like complex portfolio financial data on our small laptops, or even more mundane things, trying to navigate the world, that's geodata, monitoring our heart rates, or oops, I forgot to launch my timer. 1 minute less. But anyway, the thing is, it's all on tiny screens, and it's a limitation. It's 2D, there's not much screen space, and there are a lot of like cognitive problems, like if something is out of our sights, well, out of your sights, out of your mind, so you'll forget about it. And when you're doing analytics tasks, or like trying to solve problems, if you all of a sudden like miss a window of an important visualization thing, well, too bad, you've lost it. So it's not all like dead. So because there is mixed reality technology that is kind of appearing. So you might have heard about the Apple Vision Pro and everything, but actually it's been happening for a few years. There's a lot of like big tech companies like Meta and Microsoft that have been working on trying to deliver like mixed reality displays, so augmented reality and virtual reality displays. They primarily aimed at like watching 3D videos and playing video games, but I've been working with these technologies and a wide of different industries to try to see how we can use that for data visualization and data understanding, and especially how we can use like spatial computing, so the world around us, rather than these tiny little screens, computer and phones. So I just want to talk about a few research projects that I've designed and distributed and studied in this space. And I'll start with the very, very first kind of project that I've conducted, which was this. Oh, yeah, there you go. I need to sorry, to mute this. Otherwise, it's going to be double annoying to hear my accent voice. Okay, so here this is me. I designed this software that I call iMaxis, and it's designed to help data analysts and data scientists to explore visualizations without programming, because you sometimes have to program to leverage data and this type of stuff. So I designed with my colleagues what we call a spatial grammar. I won't try to sound like a lecturer tonight, but basically some gestures that make sense, that allow you to grab data dimensions and create visualizations. So if some of you are visualization nerds, you might recognize some palette coordinates plots, some very mundane 2D scatter plots, but we can do some cool stuff. We can connect data within views, and we can create 3D visualizations as well, because VR is also a 3D stereoscopic display. So it makes sense to see this 3D data like that. And it's very fun. So it looks like a toy, but I actually deployed it in the state of Maryland with some colleagues of mine, from UMD, University of Maryland. And we actually had like 100 data scientists working with that. And I can point you at the paper, but they made some really cool discoveries, but not with this data. That's kind of a toy data. That's a wine data set, just for the fun of the demo. The next thing I want to talk about very quickly is we learned a little bit for that. So people found it super cool. So I'm doing gestures and explaining data and swimming in data. It's awesome. I've got an infinite screen space, but it can drive you mad as well. Like you need, as a matter of fact, you need constraints to it to work. But also there was this lack of tangibility in real world. So that's an interface we sort of developed after iMaxis that leverages sort of the real world. So this is seen through the Microsoft HoloLens. So you have like multiple people working with data, and this time we physicalize the control, and people can assemble like data properties and create visualization and understand stuff together. And that was a pretty cool project. And in this very specific setup, we were very interested in how people collaborate with data. Because we have that vision that, I'm just by myself working on my tiny little computer trying to understand data. But when you think about it, it is very much of a collaborative process. We share our insights. We say, hey, I found this, etc. So we try to put people together around the table and see how they deal with complex and abstract data. Okay, a bit of a warning. The next one is not that abstract, really very, very real. It's about immersive autopsies. So a bit of a warning, there is a digital scan of a dead person, but it's a real dead person, but it's not the real rendering, but it's a rendering of a CT scan of that person. So I showed all that crazy stuff to the Victorian Institute of Forensic Medicine in Melbourne, and their job is to try to understand how people die, right? So sometimes they find a dead person and they're like, what happened? Sometimes it's very straightforward. You have a knife in the heart, so okay. But sometimes it's not that straightforward. And the data they deal with, your advice, it's not to go, but if you really can't stand that, I would suggest you, it's not that bad, but just the same. Anyway, do what you want. We designed this interface with my student, Vahid Youssef, which leverages this mixed reality interaction, right? So if you need to look inside the heart to see what happened in the heart, you just put your hand into the scan. So this is literally visualizing the MRI scan of the full body, real scale, and we render those highly responsive voxels. That's a few million data points. So there's a little bit of computer graphics and stuff in that as well. And we interact real time with this type of data. So just to give you an idea, today they really don't have that. They don't have those interfaces. They have this tiny little screen. They might see their keyboard. Some of them are not 3D visualization nerds, so they struggle. Then we designed that for them. We love it. We want to buy it. We're like, well, give us money then, and we want to do that for you. So it's a very, very cool project. Way less extreme than that. I'm also designing immersive visualization for running. I know that sounds weird, but I don't know if some of you run, but I run. I've got my watch that tells me I have 1 minute 50 left. And again, that's a typical example of I'm doing a data-driven activity. I'm running around, and I have to, I'm looking at my pace, etc. And it's a bit annoying because it's disrupting, and so forth and so forth. You might understand that if you're a runner and you have one of your verses. So that's the work I'm doing with one of my PhD students, Leon and Lee, and you might recognize the running track at YouTube. So we very kindly ask people to put a headset on their head and run around the track. That's my student. He totally owns that research. He did an amazing job. We had 30 people running around the track. And we tried different visualization design because We can display the data right in front of you in mixed reality, or we can display the pace data, for example, embedded on the track. This is a design where we see the pace data embedded in the track. Hopefully you see it everywhere. Or we can design sort of like more fun type of interfaces where people have to be there at the right time. So they make sure they have the right pace. So the paper is still under review. I hope it's accepted at a very nice user interface conference, and we'll probably try to open that and make it available for the community. People are crazy enough to run with a mixed reality headset. It works. It's much better than the watch. We have the science to prove that, or to provide evidence that it's better. Oh, this is awfully small. So I'll try to go very quick. What are the big challenges? I'll try to be very concise, but this technology is super cool, but it's also very limited. I don't know if you're familiar with how it's built, but it's a stereo, sometimes optically see-through display. There are some problems, like 1 out of 10 people still experience nausea, even though like they're really trying to make this interface a bit better. But there's still a lot of work, and I'm actually collaborating with Meta to try to understand what makes people sick when they use these interfaces so we can design better stuff. The other thing is interaction design. I sort of showed like different ways of interacting with data in these environments, using our hands, running around, walking around. It's all cool and everything, but we're still really not so sure about how to efficiently design interaction, right? We think about it in terms of like personal computers. We're sort of like in 1968, like in sort of like kind of thing. We still don't know what's the best interface for that. And a very, I mean, for sure, it's a challenge, like how does like spatial computing and AI integrate together? So how do we combine an augmented cognition with augmented spatial abilities? That's a huge challenge. Thank you very much. Oh, if you want to play, like if you're sick of your like spreadsheet and Excel and stuff, you can download Maxis with this QR code and have fun with it if you have a VR headset. Thank you very much. That was my talk. Yeah, thank you.
Thank you so much, Dr. Maxime. If you haven't had a chance, please do scan Dr. Maxime's QR code there if you need to. Before I.
It's free.
It's free. Get on it. I'm always really fast. I'm not a sports watching person, but when I do watch a game, I'm always so fascinated by and very impressed by the visualization of the game in when they do this, you know, when something's out or they need to go see the thing, to see if the ball is out. And then the visualization that then comes up, probably very simplified to what you're working on, Dr. Maxime. So sorry if that is a very simplified version of what you do, but always very, very impressed by the data that they're using and showing that in real time at games. It's pretty cool. All righty. Our final speaker for the evening is Dr. Dia Adhikari-Smith, a research fellow at the School of Chemical Engineering. Dr. Adhikari-Smith will discuss the challenges and opportunities in advocating for low and zero emission technologies to reduce emissions in heavy vehicles used in transport, construction, and mining. She will also emphasize the essential collaborations required to achieve these goals. So please welcome Dr. Dia Adhikari-Smith.
I hope you can hear me. Thanks, Janita. Just to introduce, I actually belong to two schools. So I am part of School of Chem Eng and also part of Civil Eng. So I don't want to miss out acknowledging that I'm part of the Transport Engineering Group and Civil Engineering as well, but mainly in UQDL Centre, which is School of Chemical Engineering. So for the final topic today, we'll be discussing decarbonising heavy vehicles, which literally means transitioning our fossil fuel powered heavy vehicles that we see every day, or might not see some of them every day, to lower and zero emission options. So why are we looking at cutting emissions and decarbonising different sectors? We already know that as climate change intensifies, countries around the world are setting very ambitious targets, developing roadmaps to decarbonise different sectors, cut emissions from different sectors. But are we on track to achieve this target of net zero by 2050? So and unfortunately we are not. So that's the short story, that we are not on track to achieve net zero by 2050. So if you look at the climate action tracker here, it shows that based on the current targets, based on the current initiatives, current reforms, current strategies nationally countries have in place, we'll actually be 9% above. So our GHG emissions by 2030 would increase by 9% compared to 2010 levels. But what we should be doing is we should reduce GHG emissions by 45% by 2030 if you want to reach that net zero target. So something's not working. Of course, the roadmap, the objectives, the targets that countries have in place are not working. You can see here, only 5 countries, 7%, are in the acceptable range of the frameworks and the objectives that are in play. So just broadly what I do, my focus is on emissions from heavy vehicles. So heavy vehicles you see every day on road can be buses and trucks, or it could be heavy vehicles non-road, which could be aircrafts, marine vessels, so ferries, which you see every day, or could be ships and trains. And another sector which people generally forget about when talking about non-road heavy vehicles is non-road diesel equipment and machineries used in construction and mining sectors. So it could be wheel loaders, it could be excavators, it could be cranes. They are all heavy vehicles and they all give out emissions. So when we talk about emissions, the main objective or the main push or the most articles we see every day is climate change, and we need to reduce and cut out emissions, which are greenhouse gases, GHGs. But we tend to forget that there are other kinds of emissions coming out from these heavy vehicles as well. So these are air pollution emissions. Most of these heavy vehicles that we see every day, buses and trucks, are mostly in urban areas, and these air pollution or exhaust emissions are what are impacting our health and having adverse effects. So we need to remember that there are 2 objectives: climate change and health impact. 2 types of emissions: GHG emissions and the noxious air pollutions that we need to minimize. So let's first look at the transport sector. So transport sector is a major contributor to GHG emissions. So around a quarter of GHG emissions come from the transport sector. So broadly 60% from passenger vehicles and around 40% from freight vehicles. What about the construction sector? We're also, just to clarify, I'm not talking about the mining sector today. Most of the mining projects are under non-disclosure agreements, NDAs. So I'm just going to talk about construction and transport today. So as you can see, construction sector is also very close to transport. So if you combine the construction and the building sector together, they contribute to around 23% of global GHG emissions. Among the from the 23%, around 5.5% is from the construction equipment and vehicles and machinery used on site. So our research shows that there are 3 major emission sources at a construction site. It's the construction equipment and vehicles used on site, transport to and from the construction site. So transport could be transport of materials, transport of equipment, transport of waste, definitely transport of people coming into work to the construction site and leaving the construction site, and on-site energy use. So those are our focus points when trying to decarbonize our construction site. So we work on multiple projects when it comes to heavy vehicle decarbonization. I've taken a snapshot of some of our research projects currently ongoing As you can see, do feasibility studies, we do emissions modeling, economic modeling, roadmap and policy modeling. Most of our projects are in collaboration with the state and the federal government, and a little bit with the councils as city councils as well. And we also work with industry for certain specific road mapping and policy in industry decarbonisation. And we can see most of our projects are technology agnostic. So we are not one of those that bias towards battery electric or bias towards hydrogen fuel cell. We are technology agnostic, so we include all possible low and zero emission options. So it's not always, not everything can be zero emission just tomorrow. So we look at the best possible ways to transition to a net zero future. We look at electric, we look at hydrogen, we look at advanced biofuels like renewable diesel, hydrotreated vegetable oil. There's also a very interesting project with hard to decarbonize edge user cases where we look at electric biofuel range extender vehicles. So we also do real world trials. So we are involved with certain industry and government partners where we trial these zero emission vehicles or trucks or construction equipment on site, collect the data, analyze the data and see if it is possible, what's the cost involvement, because costs always a factor. So we need to analyze all the economic modeling part of it and the operational feasibility part of it. So just a quick snapshot of what's happening in transport, what we're doing. It's a very broad sector. We have all different vehicle types, as you can see here. I've included the light vehicles as well, but there's some other researchers working on light vehicles. I'm mostly focused on heavy vehicles in the transport space. And what we can see is we're mainly focusing on the two main candidates for zero emission battery electric and hydrogen fuel cell when it comes to vehicles like buses, trucks, ferries, and trains. However, we are also doing ongoing research in electric road systems, battery swaps, advanced biofuels, SAF, which is sustainable aviation fuels, hydrogen-based shipping fuels. That's not for ferries, but for long-haul actual ships, for various heavy vehicle transport applications. So I'll take an example of, say, road freight, so trucks. So for trucks, we can definitely say, based on our research, battery electric trucks are leading in the race in all respects compared to hydrogen fuel cell trucks. They are more energy efficient. They are nearing TCO cost parity, so total cost of ownership parity. The light and medium duty trucks are already on parity with diesel trucks, and heavy duty trucks will very soon reach parity based on the subsidies and incentives in place. The problem with hydrogen fuel cell trucks, yes, they offer a potential solution for long haul, but the problem is the cost barriers, the energy efficiency, and of course, green hydrogen. We don't really have a hydrogen infrastructure. We don't really produce much green hydrogen. If it is available, it comes at a cost premium. So we need to remember all these factors when doing our feasibility studies. Globally, there are several countries which are doing excellent when it comes to decarbonizing heavy vehicles, especially in public transport like buses or in road freight like trucks. And they have decarbonization strategies. They have broad policy support. They have set targets like 30 by 30, 30% by 2030, 100% by 2040. However, Australia lacks a lot when it comes to decarbonizing heavy vehicles. We do have a lot of momentum going in light vehicle space. We have a national EV strategy, which is more focused on light vehicles. So we are pushing for a national heavy vehicle decarbonization strategy as well. Not saying it just needs to be EV, but it needs to focus on decarbonization, like a stepwise decarbonization, and we need support in policy like regulatory policies, incentives like monetary policies as well. For construction sites and construction site decarbonization, we do a lot of collaborative work with industry, specifically with Lendlease, which is a global construction company. This is a photo here from recent research with Lendlease, where we looked at Lendlease's pilot project of fossil fuel-free construction. This is One Sydney Harbour project, basically 3 residential towers, R1, R2, and Waterman's Residences, which is R3. So we collected data from the building and construction of residential tower 2, R2, and R3. R2 used all diesel-powered equipment and vehicles. However, we replaced and substituted quite a few of these vehicles and equipment with electric alternatives for R3. So we collected data. It was over the 2-year time period that these 2 buildings were built. And we collected data on energy consumption. We collected data on carbon emissions, operating costs to evaluate and understand how easy or how difficult it is to decarbonize construction sites. What do we need? What help do we need from the government? What collaboration do we need between original equipment manufacturers, between policymakers, and the construction industry in general? So, of course, the push is the same as transport. Our push is towards electrification. However, construction is a hard-to-abate sector. It's very, very difficult to decarbonize. There's not many heavy vehicles available in electric or hydrogen models. So the focus right now is a transition to a lower emission option. So use renewable diesel or hydrotreated vegetable oil to bridge the gap while the electric models become available. Same as transport, we need a lot of support from the government, policy, infrastructure upgrade, regulatory and standard upgrades, incentives, and workforce development. So altogether, more or less same for construction and transport when it comes to policy development and help to push towards these decarbonisation of heavy vehicles. I think that's all from me. Thank you.
Thank you so much, Adhikari Smith. And thank you to all of our speakers. We are coming up to the panel discussion. Nina and Hayden are just going to get the chairs ready for us. Now, if you haven't already, can you just click through the next slide, Nina, there? Thank you. Yes, this is Hayden. But yes, please use the QR code to put your questions through. Otherwise, you will, for the people in the room, you will have an opportunity to ask your questions in person as well. Lovely. Perfect. I think we have an A+ team here. I can kind of see, Dr. Adhikari Smith needs to get us to zero emission by 2050. Dr. Cordeal can help visualize all of that data. Dr. Doherty can use her words to reimagine our future. And we'll throw in some galaxies in there, Dr. Hallett, for visual effect. All right, speakers, please take your seats.
I'm sitting recording there, we spoke.
Nina, are we using the microphone?
Yes.
Yeah.
YouTube will show that one. You keep that one. Keep that one. And then you share. Oh, but yeah, Hayden, I'd like to introduce Hayden, probably your personal portfolio and we'll be today.
Very good. Thank you, Janita. I'd just like to echo her comments. Thanks to all the speakers for coming out tonight. It's fantastic to see that UQ is making some groundbreaking research and kicking goals. It's from a diverse background too, all the way from human organoids to journalism to exploring deep space. We're really covering it all. So we've had a bunch of questions come in online, and I'm sure there's some burning questions in the room as well. But I'm going to kick it off tonight with a question to Sky as well. So what skills do you feel young graduates need to be adaptable to the future of journalism?
So the future of journalism, I think that there's some really fundamental skills that are journalistic. You need to be curious about the world. You need to care about it. You get up as a journalist in the morning and you're a little bit angry because you want to fix it. So that curiosity, the willingness to speak to people, kick the tires on things, and you need to be a bit tenacious. So all of that stuff, that normal stuff. You need to be able to write, you need to be able to write top line. And you need to increasingly understand the language of code and computers, because you need to be able to translate these ideas into stories that people understand. And those stories need to be able to adapt to the technologies that are coming. So you need that. But I would also say you need to be able to push your storytelling forward. You don't want to, a lot of media companies are suffering from this. They adapted. They said, okay, there's this great social media, let's do what they want. Look what's happened. So you need to push it. You need to understand the affordances of those technologies, understand how they work to tell the public interest stories that are important. You need to serve the public interest and use the technology in service to that.
Fantastic. Thank you. So Hannah, we're working with the brain, and I know there's a few people that have been thinking about this tonight. Can brain organoids think?
That is a very good question. And it really depends on your definition of thinking, right? So we know that the brain organoids have electrical activity. And this is also, you can break it down into frequencies like your alpha waves and your gamma waves, which is what we all have, you know, when we're focusing on something or when we're sleeping. So the organoids have all this, but there are other cells in the human body that also have electrical activity, like heart cells, and we grow those in the dish all the time as well. So it's got to be more than just electrical activity. I'll actually mention there was a really sensational paper that came out a couple of years ago where a lab group claimed that they'd taught brain organoids how to play the video game Pong, right? So they wired up these brain organoids to a little computer, and the brain organoid played Pong. But then you start worrying, oh my gosh, are these conscious, you know? And there is a lot of research going into whether or not brain organoids are conscious or not. At the moment, I think we're a long way away from having brain organoids actually being conscious. I don't really think that that's something we particularly want. But yes, I think we're actually closer to having AI being conscious than we are to having brain organoids being conscious. But there's a whole nother field where people are thinking like, well, you know, AI might, you know, do us all in. If we have brain organoids that also have a physicality, then maybe brain organoids are going to be a better way, that like a biological computer. So, you know, it's a good question, and you know, there's a lot of different aspects there. But right now, I don't think so.
Yeah, interesting. So the next one has come from online, and it's for Dr. Dia. When you mentioned that battery electric is more efficient than hydrogen for trucks, does that account for long-haul journeys given the lack of recharging infrastructure currently installed?
Well, a new questions coming for battery electric versus hydrogen. That's the burning question I get all the time whenever I present. Well, yes, battery electric has certain drawbacks. In Australia, currently, we don't have proper recharging infrastructure for heavy vehicles. The recharging infrastructure is mostly focused on lighter passenger vehicles like cars. However, it's progressing really swiftly. It means in Europe and North America, they have megawatt charging that's being established. Megawatt charging is only going to take 30 minutes for a 400-kilometer driving range top up for heavy duty trucks, long haul. And the 30-minute break is enough for a driver's manual mandated brake when they're driving long distance. So it's going to be there. We are not there yet, but if we compare it to a hydrogen fuel cell truck, we don't have any hydrogen refueling infrastructure right now in Australia. So we can't really talk about, we don't have heavy vehicle or heavy duty truck long haul charging infrastructure when we don't have any hydrogen refueling infrastructure currently in the country. And I want to make it clear that green hydrogen is essential part of decarbonisation. Yearly, globally, we use around 100 megatons of grey hydrogen for different industries like chemical and manufacturing, steel making, concrete making, and fertilizer making. And how much green hydrogen did we produce last year? 100 kilotons. So 0.1% of the hydrogen that is currently being used for other sectors. So any green hydrogen we produce, we need that. But we first need to prioritize and decarbonize the sectors that are already using hydrogen. Why do we want to use it for sectors that are okay transitioning slowly using battery electric? If we have excess green hydrogen, we'll use it for sectors that currently don't use hydrogen. But we already have sectors using hydrogen that need to decarbonize into green hydrogen. That's all. Yes, green hydrogen, if we have infrastructure, if it's at cost parity, we can run hydrogen fuel cell trucks on those.
Yep, and I think that argument's going to keep going forward in the future as well.
Yes,
There's going to be no
yes, always.
quick and easy answer for it. But yeah, watch this space. Dr. Maxime, we've had a question here that says, do you see virtual reality, augmented reality, or mixed reality having a large influence on our daily lives in the future in the same way that we now depend on mobile phones?
Yeah, that's a question for like big tech people, but I'll try. I will not advocate, but it's a super tough question. So there is a very simple analogy, which is like 25 years ago when people started showing like around this like touch bricks that you can have in your pockets, which were smartphones. Like I still remember when my first ones was like this like very tiny brick. So that was great because it was super small with lots of buttons. Like who wants like a big brick and you think that take photos, why and everything. And all of a sudden it's like widespread, prices drop, etc. So I think my first element of answer is like, it's really hard to predict what's going to happen. What's the final shape of it? There is augmented reality, there is virtual reality. So to understand the difference between the two, virtual reality blocks out your world completely and you see a fully computer generated environment around you. Great application for gaming. Would you walk around in the street with it? Maybe, why not? Hope for the best. Hope for the best. I've just seen like there's like crazy videos, people wearing Apple Vision Pros everywhere in the US and stuff like that. So Apple first saw like a great opportunity. Look, I think it's amazing. And then all of a sudden the camera switched off and everything, and people starting like, having accidents and stuff. Like, stop using this, stop doing this. This is crazy. It's actually not a real device. So then there was a very interesting communication things happening here. Like, is this like, do we have the technology that allows us to use it every day? I don't think so. And maybe it will be AR, maybe it will be MR or something like this. I don't know if anyone remembers in the 2010s, early 2010s, Google came with their Google Glass. And so a lot of celebrity were wearing them. And all of a sudden people were saying like, what's that camera on your face? Like, are you taking pictures of me? But very funny, like 5 years later, it's okay to, in a pub, just like take your phone and take them pictures. No one's going to come and punch you in the face, or maybe they will, but it's less likely. So this thing completely died off, and it's hard to tell. I think there are industries like the training industry, training people for health and safety on workplaces. That's absolutely used in these environments. Medicine, they're like the first like open heart operations augmented with like live CT scans, like so very niche applications like maintaining aircraft for defense or even civil programs. That's happening. The day-to-day running with my MR glasses, I want to, but I need the technology for that. Yeah, that's my answer.
Certainly in my industry, we're starting to roll out virtual reality for training. So just like you said, and emergency evacuation procedures as well. So it is, if you said that to one of the workers at my job 20 years ago, they'd probably laugh at you. But now it's being rolled out.
The smartphone effect.
Yeah, exactly. So a question here for Dr. Hallett. It's a pretty loaded question. It says, from Carl Burton, importantly, if we are only seeing light from the past and the universe has been expanding, could it already be shrinking?
That's just where.
Okay, that's a very I guess philosophical question in some sense. So yes, it's true that when we observe distant galaxies, the light takes a finite amount of time to travel to us. So when we observe the sun, for instance, we're observing the sun 8 minutes ago. So on one hand, there's kind of a question about, does it really matter? So the point is that light is, as far as we know, the fastest thing in the universe. Information cannot travel faster than the speed of light. So if the sun were to explode now, people argue, well, we wouldn't know, and it would have already happened 8 minutes ago, and we would only see it 8 minutes later. But the fact is that to us, it doesn't matter because the hot shockwave is going to hit us in 8 minutes, right? So you can ask the same question about the universe as well. So does it really matter that we're observing it in the past? Because as far as we know, we can only interact with stuff at that finite time anyway. And then there is the other question of, a more general question of what is the universe doing now? Like, is it expanding? Is it shrinking? And so that is a somewhat open question. We know we can measure basically, or we can extrapolate how fast the universe is expanding today. We call that the Hubble constant. And this is basically tells us, how fast the universe is expanding and since the Big Bang. However, that expansion rate is not constant. In fact, if we look at different points in the past, the universe is expanding at different speeds throughout its history. And one of the really interesting things that we've found with the really latest data, it came out in April, actually, it's a bunch of papers by the Dark Energy Spectroscopic Instruments, was that actually it does seem like the universe's expansion was accelerating due to this phenomenon we call dark energy, but actually that may be turning around now. And so it could be that the universe in the present day is it's expanding, but it's not expanding as an accelerating rate as it seemed to have been, 2 billion years ago. And what does that mean? Well, it could mean that the universe will slow down until it sort of stalls, or it could mean that the universe turns around and starts recollapsing in 5 billion years in the future. The fact is we don't know, and that's why we want to understand exactly what dark energy is so we can predict exactly what it will do in the future.
Cool. And follow-up question. Do you believe, in your expert opinion, that there's life out there?
So I have given a public talk before. I gave it a couple of years ago where I titled it Why I Think Aliens Exist and Why We'll Never Meet Them. So the answer to that question is in the title of that talk. As I presented in my talk, we know that there's at least 2 billion galaxies in the universe. Each of those is similar in size to our own galaxy. And we know that our own galaxy contains on the order of 1 billion stars. If you multiply those two numbers together, you get something which I can't pronounce, but it's a very big number. And we also know from other studies that basically every star, or nearly every star in the local universe, or at least within our own galaxy, contains planets. None of those planets we are aware of contain life. We think there's really very specific conditions that are required for a planet to develop life. But just in pure numbers, I think it would be, I would say that the numbers are there that mean that there probably is life elsewhere in the universe, just in terms of how many stars there are, how many planets there are, how many galaxies there are. That said, as we've already established, the distances between these galaxies is absolutely vast. When we're looking at galaxies, that light has taken billions of years to reach us because those distances are so vast. That means if those aliens were to send signals to us, those signals would also take billions of years. I don't know if we'll be here in 1 billion years' time to hear them. I don't know if the aliens are there now or were there 1 billion years ago. So, it's whether or not we'll actually ever communicate them is a different question. I think the answer to that is almost certainly no.
That's a good thought-out response. So I'll open up to the room. We've got a bunch of questions coming in online, but if anyone's got any burning questions they want to stand up and ask the panel, I can keep reading them out online otherwise. Yep.
Doctor, I noticed a few EQS operations were in Chile. Particular reason for that location?
Yes, so Chile is a really good site for telescopes. It's extremely high latitude. The height off the ground.
So it's very mountainous. Those two telescopes that I showed are both situated pretty near each other in the mountains in Chile. And then in addition to that, it's also very dry. So one of the big issues when you're trying to observe space is rain and clouds. If you don't have a space telescope, they get in the way. And so Chile is both very dry and very high, which means you have less atmosphere to look through. And so there's a few places on Earth which are as good. Another really famous example is Hawaii. So Mauna Kea in Hawaii is an excellent place for a telescope. In fact, it's so good that the weather there is amazing because when you actually, when you put a telescope on a mountain, you don't have to worry about half of the weather because you're above the clouds. And so that means that you get amazing conditions. There's very little atmosphere to look through, but also you get better weather on average. By comparison, we have a telescope in Australia, which is a 4-meter telescope. It's the same size as the Dark Energy Survey telescope and the one used for the Dark Energy Spectroscopic Instrument. They're actually kind of triplets. They're all built around the same time. And that's in New South Wales. And the conditions there are unfortunately not quite as good. It's a bit rainy, unfortunately. You know, Australia doesn't really have any high mountains. So we have to look for a lot of atmosphere, and it's noticeable in the images we take. They're more blurry because we have more atmosphere to look through. So yeah, that's why we chose Chile.
Great question. Thank you. Sky, can you explain more about the research projects behind Wicked Thinking?
Oh, yeah. So those two issues are based on two projects. The first on forced migration was a collaboration with the Digital Cultures and Societies Hub, which is in the HAS faculty. And they were collaborating with the UNHCR, and they want to think about the future of migration. So these were questions that they posed to us. And so we ran a 2-day workshop using design methods and creative writing methods to try and get the people in the room who were in the humanitarian sector and also some academics and people in media as well to start thinking about that. So the responses and that work informed that, also with interviews with the UNHCR. And the FIRE one is a project that's been running over the last couple of years just up in the D'Aguilar Range, which is at risk of very high levels of bushfire intensity. And that's been a couple of years project where we've been interviewing people. We did some future focused collaborative co-design workshops and about, you know, what could a future resilient fire resilient future look like, and how does a community work with agencies and that kind of thing. So that all that data feeds into these things. We get these kinds of projects normally, particularly the bushfire one, we'll get traditional research outputs out of that, papers, that kind of thing. We also get non-traditional research outputs like our design materials and the tools that we use. And then this is a more experimental output from that, but it's all informed by those research activities, which are, and particularly in the bushfire one, those photographs are all people burning fires on their land, and it's all from that area.
Thank you. Hannah, do you think that organoids can be used on a wider scale? And I'm assuming the user here means beyond the brain. And if so, how?
That's a really good question. I'm not quite sure how to answer it. I think the most appropriate example would be what I touched on before, where we could theoretically use these brain organoids as a computational power, and that would let us, you know, crunch some numbers faster than what computers can currently do. But a lot of, like, that's quite theoretical at the moment, I think. Most of the applications are generally based on health and what the challenges are right now, which is generally people with some uncurable neuronal disease that we don't understand. Yeah.
Awesome, thank you. The next question here I've got is for Dia. A lot of your research involves real-world trials like the fossil fuel-free construction site. Could you share some highlights or learnings from projects like these, and maybe how they'll interact with us in the real world and the way that we live, work, and play?
Right, so an opportunity to collaborate with Lend-Lease on a real world project is brilliant for a researcher because most of the times we look at future scenarios and we are modeling and simulating and trying to project what the future will look like and what it'll happen or what the costs will be like, making assumptions. So having an actual real world trial is always beneficial to collect real world data and analyze the data to understand what actually happens at a construction site. So when we collaborated with Lend-Lease on One Sydney Harbour, one of the buildings, R2 building, we used all, as I said before during the presentation, all diesel equipment and vehicles. So we replaced some concrete pumps with an electric concrete pump. We replaced the tower cranes with electric tower cranes. We replaced hoists and elevated platforms. I'm not going to name all the construction equipment and boy, but yeah, so we replaced a lot of them with electric alternatives, whatever were available in Australia. It's very difficult. Model availability is a big barrier in decarbonisation in Australia. We're so far off and we don't manufacture these here. So getting them here is the biggest problem. So collecting the data, normalizing the data and analyzing it to understand, like we saw there was like using, say, for example, electric concrete pump, using it, there was 60% more energy efficient compared to a diesel concrete pump. The operating energy cost savings were around 70%. When using an electric concrete pump, the emission savings, like the carbon emissions, were not as high because we were using the current Australian grid, which is not that green. So the current Australian grid numbers around 19% renewable. So the carbon emission savings were only around 13%. But of course, our grid's becoming greener. We have targets for a greener grid. At least in Queensland, it's very soon. We have an 80% target. So as the grid becomes greener, we'll have more carbon emission savings as well. So getting these numbers and showing how we can work with electric alternatives in real world situations and how that's beneficial, not just for the people living the community, because most of these constructions are in urban areas. We'll have so much construction here in Queensland, in Southeast Queensland, because of the Olympics coming up in like 8 years. So all this construction will happen in urban areas, and we need to at least not decarbonize, it's not achievable, at least lower emissions using different methods and techniques and reforms and policy. So getting this pilot project where we trialed them, collected data and showed it at different seminars, international conferences, in government meetings, how it can help is, of course, pushing and driving the policy to make these changes.
Fantastic. Thanks so much. We've got time for a couple more questions. And so I've got one here for Maxime. Obviously, a lot of your work involves handling data, and whether that's data that's numerical or if it's data that's collected from the VR modules that you're developing itself. The question is from Janita. What have been some of the most surprising user feedback or insights you've received when testing your immersive data experiences?
Yeah, nice question. Maybe I'll try to explain a little bit more like the research context and to contextualize a little bit what we try to do. So the big research problem underneath is understanding data, and we hear everyone here actually talking about, I mean, a lot of people on the panel talking about data, and there is a lot of problems involved with data. The problem is, like, you need to be an expert of the domain. I mean, as in you have to understand what this data is about. That's the first thing. That data may as well like concern you, like, it might be a construction site thing and you live right next to it, but you have no idea about structures and whatever, but it concerns you directly, right? The second hurdle is how do I turn, like, things that live on servers and clouds and stuff into insight? And so the mixed reality stuff that I was showing before, it's all fun and everything, but it's really about breaking this barrier, right? Because today your interface to this data is like, again, Amazon Cloud, whatever, some super hardcore Python or R, whatever programming interfaces, trying to derive that. Once you've got that, once you've got interface, if you're not too bad, you're pretty good at modeling, pretty good at visualization. And then maybe if you're good in the domain, then you'll try to understand some insights. So that's just trying to explain the research thing. And so when I run these different research experiences, so I'm like, right, okay, that's pretty complex data, and that's a pretty complex programming interface. Let's think about a solution. I've done a lot of projects without immersive experiences. But with these immersive experiences, what was very interesting is like you can clearly see the effect, not necessarily in terms of infight, but you can clearly see this friction effect that goes away. Like when you have like a natural user interface to the data, as in you don't have the hurdle of like menus and input styles, etc. When you can directly touch a data point and just query the information about that data point, it's a very, very different process. So I've published like over 60 papers on that and on user studies. There's like some very specific insights that have been made for econometrics, for example, people working in the statistics, the Bureau of Statistics in Maryland, things they never knew they would find. Probably some dodgy use of federal budgets, I think, simply because like finding outliers, detecting these like very important data features require a lot of like, again, like, programming interfaces or being an expert with the data. So that's the thing that's interesting. But the thing I really want to say, and that's a very long-winded answer to get what I want is like, actually the most interesting thing I found is when we show this to kids or younger people, because they understand what data is, right? Like you collect your data with your phone or with your watch and this type of stuff. Oh yeah, I get that. And then you can see where you've been today and how long you've been walking and how long you've been awake, etc. Oh yeah, that's great. And like having an interface for kids to really access the data without having to learn how to program. I think it's very important. Everyone should learn how to program, but I also think we need like less friction to data and to insights. And the other thing I just want to sort of like finish on is like there is AI right now, and AI is supposedly like if you think about it, it's about efficacy, right? It's about efficacy to get to the insight. And you would say, why the hell do I need like a VR environment with data points everywhere where I can check that into an LLM or some fancy AI thing where it does all the visualization, insight, derivation, etc., and just produces an output and says that's it. So that's a big question. Is it better than spending hours in a VR environment trying to make sense of data? Well, it's a kind of the $1 million question or $1 billion question at the moment. So yeah, thanks.
Thank you. And so we've got time for one more question, and it's going to be for Dr. Howlett. What is the criteria for a galaxy to be classified as interesting?
Okay, so all galaxies are interesting. Okay, just put it out there. So with that image that I showed, so for those galaxies that I identified in that image, the reason we called them interesting in particular was because we were able to follow them up with the DESI instrument and then calculate how far away they are. So there's many caveats which go into being able to calculate how far away a galaxy is, but many of them are basically, can we observe it in a reasonable amount of time to a good enough sort of, I'm going to use some terminology here, but signal to noise. So basically, can we get enough signal enough light from that galaxy down the fiber in a reasonable amount of time so that we can observe its properties? Some galaxies are much easier to do that than others. And in particular, to give a bit of context, the way we actually measure how far away these galaxies are is we take the light down the fibers of each galaxy. We then run it through a prism, so effectively like to create a rainbow. And then you look for features in that rainbow that tell you about the chemical elements in that galaxy. Certain galaxies have different compositions, and certain chemical elements are much easier to spot. And so in particular, things like hydrogen, all across the universe, many galaxies contain hydrogen, and some galaxies contain so much that when you observe the light, you see an amazing feature of hydrogen. And so we then go, well, we know we can get distances to those galaxies really easily. if they've got a lot of hydrogen. So is there a way that we can use the images we got, so the colors basically, to say, well, these galaxies are probably going to have a lot of hydrogen. So that's what we do. So certain types of galaxies we know have lots of hydrogen. There's another class which I use in that image, which have a lot of calcium. And so that's also another very easy feature to see in those galaxies. But typically the calcium-rich ones are very red and they have lots of old stars. And then the hydrogen-rich ones creating lots of new stars all the time. And so they are very blue. So, we use different colors to identify different types of galaxies from those images that we want to follow up later.
Great. Well, thanks so much to our speakers. If you wouldn't mind joining me in applauding our speakers for their Q&A and presentations.